There is a moment sitting inside a Shinkansen at full operating speed when the experience feels wrong. The train is traveling at 300 kilometers per hour. Outside the window, the landscape is dissolving into a blur, and inside the cabin, there is almost no sensation of movement. No vibration in the seat, no swaying, no noise beyond a low, steady hum. A car on a highway at 120 kilometers per hour feels more turbulent than a bullet train at more than twice that speed. That disconnect between what you know intellectually and what your body is telling you is the result of engineering that most passengers never think about and almost nobody fully understands. Because at 300 kilometers per hour, the forces acting on a rail vehicle are not just larger versions of the forces at 100 kilometers per hour. They are categorically different problems requiring categorically different solutions. Start with the most basic physical constraint. A train cannot steer. A car can turn its wheels to follow a curve. A train is locked to the track, and the only way it can change direction is if the track changes direction beneath it. At 300 kilometers per hour, any deviation in the track geometry, a slight kink, a millimeter of height difference between the two rails, a gradual change in the track's horizontal curvature, is transmitted directly into the vehicle as a force. The faster the train moves, the larger the force generated by a given geometric imperfection. Track geometry that is entirely acceptable for a conventional train becomes a serious engineering problem for a high-speed train, and the tolerances required to operate safely at 300 kilometers per hour are an order of magnitude tighter than anything used in conventional rail. The Japanese Shinkansen network, which began operation in 1964 and remains one of the most refined high-speed rail systems in the world, maintains track geometry to tolerances measured in millimeters. Dedicated track inspection vehicles run the entire network regularly, measuring rail height, gauge, cross-level, alignment, and twist at precise intervals. Any section of track that deviates beyond defined limits is flagged for maintenance before the next operational service. The inspection vehicles themselves travel at operating speed so that the measurements reflect the dynamic behavior of the track under realistic loading conditions, not just its static geometry. This level of maintenance is not a precaution, it is a prerequisite for safe operation at these speeds. The rail itself is a different material from conventional rail. High-speed rail uses continuously welded rail, meaning the individual rail sections are welded together into lengths that can extend for kilometers without a joint. Conventional rail uses bolted fishplate joints between sections, and those joints create a small geometric discontinuity and a change in stiffness that produces the characteristic clacking sound of a train passing over conventional track. At high speed, those joints would generate significant impact forces at the wheel-rail contact. Continuously welded rail eliminates the joints entirely, but it introduces a different problem. Steel expands when it is warm and contracts when it is cold. A rail section that is fixed at both ends will develop compressive stress when it warms and tensile stress when it cools. Above a critical temperature and stress level, a compressed rail can buckle laterally, a phenomenon called sun kink, which creates a sudden large geometric deviation in the track. Below a critical temperature, tensile stress can cause the rail to fracture. Managing this requires that the rail be installed in a specific stressed condition. During installation, the rail is heated or mechanically stretched to a specific tension corresponding to a target temperature called the stress-free temperature or rail neutral temperature. It is then fixed to the sleepers in that stressed condition. When the rail warms above the neutral temperature, it wants to expand but cannot, so it develops compressive stress. When it cools below the neutral temperature, it develops tensile stress. The neutral temperature is chosen so that the maximum compressive and tensile stresses encountered across the full range of seasonal temperatures remain within safe limits. The correct neutral temperature depends on the local climate and the specific rail profile and fastening system being used. The wheel-rail interface is where the most intense mechanical loads in the system are concentrated. The contact area between a steel wheel and a steel rail is approximately the size of a fingernail, roughly 1 to 2 square centimeters. Through this tiny area passes the entire weight of the vehicle divided by the number of wheels, plus any dynamic load amplification from track irregularities and vehicle motion. On a Shinkansen car weighing around 40 metric tons with 16 wheels, The static load per wheel is approximately 2.5 metric tons. Under dynamic conditions, this load fluctuates above and below the static value with each irregularity the wheel encounters. The contact stress at the wheel-rail interface exceeds 1,000 megapascals under normal operating conditions. That is more than 10,000 times atmospheric pressure concentrated in an area smaller than a postage stamp. At these contact stresses, both the wheel and the rail undergo a phenomenon called rolling contact fatigue. Microscopic cracks initiate at or near the surface of the contact zone and propagate under repeated loading. Over time, these cracks can lead to surface spalling, where small pieces of material break away from the railhead or the wheel tread, or to more serious subsurface crack growth that can lead to rail fracture. Managing rolling contact fatigue requires careful control of wheel and rail profiles, regular rail grinding to remove damaged surface material before cracks propagate to a dangerous depth, and monitoring of wheel condition at defined intervals. Shinkansen wheels are inspected ultrasonically and visually at regular intervals, and wheels that show defined levels of wear or damage are replaced before they reach a condition that could cause problems in service. The aerodynamic environment at 300 km per hour is a completely different challenge from anything encountered in conventional rail operation. The train is moving through air at a speed where aerodynamic forces are comparable in magnitude to gravitational forces on some components. The drag force on the train scales with the square of velocity. Doubling the speed from 150 to 300 km per hour increases aerodynamic drag by a factor of 4. At 300 km per hour, aerodynamic drag accounts for the majority of the energy consumed by the train. Reducing it is not just a comfort issue, it is a fundamental operating cost issue. The nose shape of a high-speed train is the most visible aerodynamic feature and the one most directly linked to drag reduction. The original Shinkansen Zero series, introduced in 1964, had a relatively blunt nose by modern standards. As operating speeds increased and aerodynamic understanding deepened, nose shapes became progressively longer and more refined. The Series 500 Shinkansen, introduced in 1997 and capable of 300 km per hour in revenue service, had a nose 15 meters long with a pointed profile that minimized pressure drag. Later designs, including the N700 series and the E5 series used on the Tohoku Shinkansen, use noses of similar or greater length with carefully optimized cross-sectional shapes derived from computational fluid dynamics analysis. The aerodynamic problem that drove the most dramatic nose shape change was not drag on open track. It was the pressure wave generated when the train enters a tunnel. When a high-speed train enters a tunnel, it acts like a piston, compressing the air ahead of it. This compression wave travels down the tunnel at the speed of sound and exits from the far end as a pressure pulse. At speeds above approximately 200 km per hour, this pressure pulse is strong enough to generate a loud boom at the tunnel exit called a tunnel boom or micropressure wave that is audible at considerable distance and causes complaints from residents near tunnel portals. In Japan, where the Shinkansen network passes through densely populated areas and tunnels are common, this was a serious operational problem. The solution was developed partly by a Shinkansen engineer who observed that kingfisher birds, which dive from air into water at high speed with minimal splash, have a long tapered beak that manages the transition between two media of very different density. The N700 and E5 series nose shapes were influenced by this observation, not as a literal copy but as a design principle. A longer, more gradually tapered nose reduces the rate of pressure buildup as the train enters the tunnel, which reduces the amplitude of the compression wave and the resulting tunnel boom at the exit. The effect was significant enough that trains using the optimized nose shape could operate at higher speeds through existing tunnels without exceeding the noise limits that constrained earlier designs. Inside the tunnel, the pressure fluctuations experienced by passengers are another consideration. As the compression wave and its reflections pass the train, the cabin pressure changes rapidly. In an unpressurized train, these pressure changes would be felt as ear-popping discomfort similar to rapid altitude change in an aircraft. Modern Shinkansen rolling stock is fully pressurized, meaning the cabin is sealed and the internal pressure is controlled independently of the external pressure fluctuations. The cabin pressure management system adjusts internal pressure gradually to match the ambient pressure changes outside, but at a rate slow enough to be imperceptible to passengers. The seals on doors and windows must maintain this pressurization reliably throughout the service life of the vehicle. Suspension design on a high-speed train has two separate functions that must be optimized simultaneously. The primary suspension, between the wheel sets and the bogie frame, manages the high-frequency inputs from rail irregularities and wheel-rail contact dynamics. The secondary suspension, between the bogie frame and the car body, isolates the car body from the lower-frequency motions of the bogie. On Shinkansen rolling stock, the secondary suspension uses air springs, pneumatic devices that provide a very low spring rate and therefore excellent isolation from bogie motion. The air spring pressure is actively controlled to maintain a constant car body height regardless of passenger load variation, which ensures that the floor remains level and that door alignment with platform edges is maintained precisely. Some modern high-speed trains use active suspension systems in which sensors measure the acceleration of the car body and actuators in the suspension apply corrective forces to reduce the motion. The Japanese N700 series uses a semi-active damping system on the secondary suspension that reduces lateral vibration. The tilting system used on some high-speed rail lines allows the car body to tilt inward on curves, reducing the lateral acceleration felt by passengers and allowing higher curve speeds without discomfort. The Shinkansen lines were built with generous curve radii specifically to avoid the need for tilting at their design speeds, but tilting technology is used on high-speed lines in Europe and on some Japanese lines where the alignment is more constrained. The traction system that actually drives the train at these speeds has its own engineering requirements that are distinct from those of conventional electric locomotives. Shinkansen trains use distributed traction, meaning motors are distributed across multiple axles throughout the train rather than concentrated in a locomotive at one or both ends. This reduces the load per axle, which is important both for track loading and for wheel rail adhesion. The motors are three-phase AC induction or permanent magnet synchronous motors controlled by IGBT inverters that can vary the frequency and voltage of the supply to control motor speed precisely. The regenerative braking capability of these motors allows a significant fraction of the kinetic energy of deceleration to be returned to the overhead supply system rather than being dissipated as heat, improving overall energy efficiency. The overhead catenary system that supplies power to the train at 25,000 volts must maintain reliable contact with the pantograph on the roof of the train at 300 kilometers per hour. The contact wire must be tensioned precisely so that its wave speed, the speed at which a mechanical disturbance travels along the wire, exceeds the train speed. If the train travels faster than the wave speed of the catenary, it creates a resonance that causes the contact wire to bounce away from the pantograph, interrupting power supply. Maintaining catenary wave speed above train operating speed requires specific wire tension and catenary geometry, and it becomes progressively more demanding as operating speeds increase. The catenary systems on lines designed for 300 to 350 km per hour operation are significantly more sophisticated than those on conventional electrified lines. So the smoothness you feel inside a bullet train at 300 km per hour is not an accident, and it is not simply a consequence of the train being well built. It is the integrated result of track geometry maintained to millimeter tolerances, continuously welded rail installed at a precisely controlled stress-free temperature, wheel rail profiles managed to limit rolling contact fatigue, aerodynamic shaping refined through computational analysis and physical observation, fully pressurized carbodies with active suspension systems, and a catenary designed so that its mechanical wave speed stays ahead of the train at all times. Remove any one of these elements and the system does not just become less comfortable, it becomes unsafe at these speeds. The sensation of stillness inside the cabin is not the absence of engineering, it is the presence of an enormous amount of it, all working simultaneously and invisibly to make something that should feel violent feel effortless. And that raises a question that follows directly from this. What happens when one element of this system fails at speed? The answer involves the emergency systems built into high-speed rail that most passengers have no idea exist, and the physics of stopping a train from 300 kilometers per hour safely is a problem with solutions that are considerably less obvious than they appear.